This video is about solving linear inequalities. So the prefix in for inequalities means not. These are things that are not equal, so less than, greater than, those types. There are a couple main ideas that we'll need and then some symbols, and then we'll go through some examples with this. We're going to say that solving linear inequalities is just like solving linear equations, but with one main exception. So we've been doing linear equations now so far with just getting variables alone to solve an equation. Well, here's the exception when we're doing linear inequalities. When we multiply or divide by a negative, we must flip the inequality symbol. For example, if we had the inequality stated as negative 2x is less than or equal to 6, and I wanted to solve it for x, which means get x alone, we would do the same kind of step as if it were an equation, which is I would divide both sides by negative 2 to get rid of the negative 2 that's in front of the x, which would leave me with just an x on the left side. But when dividing by a negative, as our note says above, this is a case where you have to flip the inequality sign around. So the inequality symbol, of course, those little carrots, and we've discussed already, those are really alligators, hungry alligators, always eating the bigger value. That's what they're doing or showing. So now it was eating to the right side, now it's eating to the left side. Of course, it's the greater than or equal to, so there's a little line underneath that, which indicates the or equal to part. And then on the right side, we have now 6 over negative 2, which is negative 3. So altogether, we could say that x is greater than or equal to negative 3, which would be like the solution to that inequality. So that's just a simple example of flipping the symbol. Whenever we multiply or divide by a negative, that's what we have to do. Now, symbols are important in the inequalities, and so we've already used one of them. Let me just review and introduce some new symbols that we'll have here. So the symbols of less than or equal to, and then greater than or equal to, amount to the carrot or alligators, and then underneath those a single horizontal line segment. And those, of course, indicate the direction by pointing or eating, a certain way. Those, in some cases, are taught through mathematics on a graphing system as represented by a solid dot. Okay, so you might see, like for x, the example we just did was x is greater than or equal to negative 3. You might see that represented where you have a number line, negative 3's on it, and then there's a solid dot for the fact that it's greater than or equal to. Well, in the new notation we're going to use, instead of a solid dot, we're going to use square brackets, and those brackets will be opening up toward the arrow that completes the rest of the graph, as we'll see. So that's the old way was the dot, the new way is going to be these square brackets. Secondly, the strict inequalities of less than or greater than, which is just the alligator mouth with no equal segment underneath, those used to be indicated by an open circle. So you might see on a number line maybe an open circle symbol at the value negative 3 like we were looking at previously. Of course, that was an inclusive greater than or equal to, so we wouldn't see the open circle there. But the old notation is the open circle for a boundary like that. But the new notation is going to be a curved parenthesis instead of that. So kind of like the square brackets, the parenthesis is going to open up toward wherever the arrow is pointing. Now let's do some examples that will use this notation and discuss how graphing works. So if I wanted to graph x is greater than negative 2, I would put just a horizontal number line, kind of boring, and then make sure that my boundary of negative 2 is marked on it. So I just have like a tick mark on the number line with a negative 2 there. Now, if x is what the alligator is preferring to eat, as this one shows, that means x is actually greater than negative 2. Remember, the alligator is always eating the bigger or greater value. Well, think of the number line as you've known it, where are numbers greater than -2? To the left or to the right? Well, on a number line, to the right would be bigger or greater. So we're going to use an arrow that starts at -2 and then goes to the right. I'll put a little arrow mark indicating the arrow keeps going to the right there. And that's going to represent all of the x's which are greater than -2. Now, given what we just said above about boundaries, this strict inequality, which does not include the or equal to, would have a parenthesis curved and opening toward the arrow. And so that's exactly how we want to label the graph for that kind of expression. Now, if I had another example beneath it here as x is less than or equal to 3/2, then similarly we can put 3/2 on a number line and also understand that the alligator is trying to eat the 3/2, which means x is actually smaller than 3/2. Smaller than would be to the left on the number line. So starting at 3/2, we put a line segment that's going to point to the left. But then this kind of inequality is the inclusive less than or equal to. So we're going to use a square bracket, and the bracket, just like the parenthesis, always just opens toward where the arrow is pointing. And so this is how we can take simple inequality statements or expressions and put them on a number line graph. Now let's do some examples where we do even a little bit more before we get to the graphing. We want to solve and then graph. Our first example here reads 3x minus 8 less than 2x plus 11. Well, as we stated way above in our notes, solving an inequality, and we know it's an inequality because this is not equals, this is strictly less than as given. Solving one of these is just like solving an equation with one exception. If we multiply or divide by a negative on both sides, we have to flip the symbol. Otherwise, all the same steps we've used for equation solving apply here. So we would distribute first, we would combine like terms on each side. In this example, there's no need to do either of those steps. So then we skip right to that third step we discussed in previous topics of variables first, smaller to larger. Notice we have a variable term on each side. We have a 3x on the left and a 2x on the right. Of course, 2x is smaller, so we'll subtract it to move it. And of course, I'll do that on both sides so that the 2x's cancel on the right side. On the left side, we have now 3x minus 2x, which is just x. And then we keep the minus 8 after it that we had there. Then we keep the inequality symbol as is, so it's a less than with an alligator trying to eat the right side as it was originally. We haven't flipped anything because we have not multiplied or divided by negative here. And then I'll also just bring down the positive 11 we had originally there on the right side. I want to get x alone, and we're almost there. I have an x minus 8 on the left side, and I could get the x alone by adding 8. Of course, I got to do it to both sides. So the 8's cancel on the left side, giving us just an x over there. And then we keep the inequality symbol as it was, the less than. So now the alligator is still eating the right side, and on the right side we have 11 plus 8, which is 19. Now we want to take that simplified, or you could say solved, inequality expression and put it on a graph, which is what we were just doing previously. So we're going to take our boundary number, which is 19, the only number we have in this inequality, put it on the number line. You don't need to go crazy and label, numbers surrounding it necessarily. You just want to know clearly where your boundary number is. And then if x is less than it, as this expression says, of course, remember, the alligator is eating the 19, which means x is smaller. So that would be to the left. We'll put an arrow to the left. And then using a strict inequality would be a curved parenthesis, of course, opening toward the arrow to the left. So to solve and graph really means we have two things as our solution: the simplified inequality, x less than 19, and then the number line graph that goes with it. Really, the number line represents the exact same thing as the inequality statement. Let's try some other examples of a similar type. Our second one reads, x over 4 is less than -1. Well, to get x alone in a scenario like this, we've actually seen this before, right? X is being divided by 4 right now, but we want to undo that by multiplying by 4. And of course, I need to do that on both sides. Now this is a positive 4 I'm multiplying by, so I don't actually have to flip the inequality sign here. The 4's will cancel on the left side, leaving us only with an x. I'm going to keep the inequality sign, which is the alligator trying to eat the right side. And on the right side we have now negative 1 times 4, which is negative 4. And so we have an x less than negative 4 as our simplified final inequality statement. And of course we can graph this by putting our boundary number of negative 4 on a number line. And then if if the alligator is trying to eat the negative 4, that means x is smaller, which would go to the left. So we'll put a line with an arrow going to the left from negative 4. And strictly less than would mean a curved parenthesis. So our x is less than negative 4, and its graph will be our total solution for this one. Let's try another example. This one begins as negative 7x is greater than 21. So in other words, the inequality sign is the alligator trying to eat the negative 7x. Well, we want x alone to have this solved, and algebraically, as we've seen with equations, we can just divide by negative 7 to get that x alone. Of course, we'd have to do it on both sides, but here we are dividing by a negative. This is a special case then where we have to flip the inequality symbol. So we now just have an x on the left side. We're going to flip the inequality symbol, so now the alligator is trying to eat the right side, which is now 21 over negative 7, which is negative 3. So we have x is less than negative 3, and then we can graph this pretty simply by on a number line putting our boundary value of negative 3, and this would indicate the alligator is trying to eat the negative 3, which means x is smaller than it, which means it's to the left of negative 3, so we'll have an arrow going to the left, and a strict inequality like this would be curved parenthesis opening toward that arrow. So we have our statement and our graph matching it as our solution. Let's try another example. This one begins as 7 minus 2, open parenthesis, x minus 4, close parenthesis, less than 5, open parenthesis, 1 minus 2x, close parenthesis. Alright, we want to solve this for x like we've been doing, and notice in this example we have an opportunity to do some other solving steps that we've done with equations before. Now we're just doing them with inequalities. That is, we want to distribute first, since we have the opportunity to do so, really on each side. There are ways to distribute into the parentheses as shown. That would result in the left side of our inequality being 7 minus 2x plus 8. We're going to keep the inequality symbol, which was an alligator eating the right side here. So we say now the left side is less than the right side, which would, when distributed, be 5 minus 10x. So after distributing, as you'll recall, we want to combine like terms on each side. On the left side, we can combine the constant numeric terms. 7 plus 8 is 15. So really we have 15 minus 2x is less than 5 minus 10x. Now we want to go to our main strategy of variables first, smaller to larger. Notice that we have a variable term on each side, but notice that both of those terms have negative coefficients. It's a negative 2x on the left side and a negative 10x on the right side. Well, if we're trying to go smaller to larger, this can be tricky when they're negative, or when even just one of them is negative. But really, negative 10 is smaller than negative 2, so we want to move that one by adding 10x to both sides. And so the 10x's will cancel on the right side. On the left side now we'll have 15, and then we have this negative 2x plus 10x, which will give us positive 8x, and that is less than, on the right side all we have is 5. So we're getting there. We want x alone. Next we could subtract 15 to work on that. That'll leave us with only an 8x on the left side is less than. On the right side now we have 5 minus 15, which will be a negative 10. And so we can divide by 8 on both sides to get the x alone. Notice we're dividing by positive 8 here, so we don't have to flip any symbol here. We're not going that route, or it's not required since it's a positive value we divided by. And then on the left, let me rewrite what we have here. There's just an x on the left side it's less than, so inequality is still trying to eat the right side, but we can reduce the right side, which is currently negative 10/8. If you divide those each by 2, you get a negative 5/4. And so that's the statement we want to put on a number line. We'll just put our negative 5/4 down. And of course, the alligator is indicating that x is smaller than it, so we'll go to the left with our arrow, and strict inequality means a parenthesis opening that way. So we have our statement and our number line that goes with it for our solution. Let's try a couple more examples. For the next one, we'll start as 5 minus 3x is less than 3, open parenthesis, x minus 2, close parenthesis. Well, kind of like we saw in the previous one, we'll begin by distributing just on the right side with this one. And so I'll rewrite that to get 3x minus 5 on the left side unchanged is less than, on the right side now we have 3x minus 6 if we distribute that 3. Well, same kind of thing where we want to combine like terms on each side. There's nothing to combine. Then we want to go variables first, smaller to larger. But notice in this case, and we've actually seen this back with the equations, the variable terms actually match on both sides. They're both 3x. So you would have a hard time picking a smaller one because they're the same. Now, if I subtract 3x from both sides, now this will leave us with a negative 5 on the left side and a negative 6 on the right side. So the 3x's are gone on both sides, and now we have negative 5 is less than negative 6. And to be clear, this means the alligator is trying to eat the negative 6, indicating that negative 6 should be bigger than negative 5. However, that's not true. Negative 6 is more negative. It's smaller than negative 5. And so in a case where the variables disappear and what we're left with is a false statement, just like we had sometimes with equations, we would have to say that there's actually no solution for this inequality. Moving on to a next example, this one begins as 5, open parenthesis, x plus 4, close parenthesis, is greater than, so the alligator's eating the left side here, and then we have 5x plus 10 on the right side. Well, we can begin by distributing the 5 on the left side here in the parentheses to get 5x plus 20 is greater than 5x plus 10. And in a similar scenario here, we notice we have the same x terms on both sides. They match 5x, which means if we subtract 5x from both sides, there isn't a smaller to pick on here. They match. Those disappear, leaving us with 20 on the left side is greater than 10 on the right side. In other words, the alligator this time is trying to eat the 20 on the left side, and there's a 10 on the right side. Now, the variables are gone here, but that statement that we're left with is actually true. 20 is greater than 10, and so this would be a case of all real numbers. Now, regarding the graphs of these kinds of answers, in these last two examples here, numbers 5 and 6, for number 5, when there's no solution, there's no graph, like there's nothing to graph. For number 6, with all real numbers, you could put a graph on it, but it would just be the entire real number line. So there's really no boundary number to put. It would just be arrows on both the left and the right side, indicating that everything is a solution. Let's try one more example. This one begins as the following. It says the distance from 0 to x on a number line is less than 3. Now, this is going to utilize some key vocabulary and definitions here. When we see distance from 0 to x on a number line, that phrase actually means, it's part of the definition of absolute value of x. The distance from 0 to x on a number line is the same thing as absolute value of x. So that's what that phrase means. And then the rest of this says is less than 3. So all we could say then, or have to say, is absolute value of x is less than 3. We're using the less than symbol to indicate this, which would be now an alligator eating the 3. And this simple answer is all we need for this. There's really no graph on this kind of thing yet. In later topics or classes in algebra, you will get to eventually a way to graph an inequality like this with an absolute value involved. There's a few more extra steps, but for now we're just writing this simple statement here, translating the language into the absolute value.